Open stack physics problem number 76 from chapter 23. And I drew the picture a little bit weird, and I'm going to explain it a little bit. But we have this, I'm going to explain it now. So here I have a battery, an inductor, and a resistor. And so we have this switch that can move right here. So if, is that how the switch goes? Well, anyway, there's a current in here, but then we've removed the batteries. Yeah, if I move this switch down here, then it's an LRC circuit with a battery. But then if I switch it to this position, then there's current here, and it's going to have it going around the circle. There's no battery. Okay. Yeah. Ooh, that's strange. Discharging. Do I have that circuit right? It said position 2. Position 2. It does not have a battery in it. Okay. That's fine. I can deal with that. And the first question says, this is a little strange. What is the initial energy in the inductor? Okay, I can do that. So to give the current of 5 amps, to give the value of the inductor, and this is what's the energy stored in there? And I'm going to call that U, just to not confuse it with electric field. So U is 1/2 Li squared. So this is just a plug-in problem. 1.5 henries. I'm kind of messy sometimes. 1/2 1.5 5 squared. So let's just calculate that. 0.5 1.5 times 25 times, because that's 5 squared. 18.75. 18.75 joules. 18.75 joules. That was easy. Okay. Next question. How long would it take the current to decline to 5%? Okay. So the current's going to decrease, right? And the thing is that we have these two equations. We have this, I as a function of t is I0, 1 minus e to the negative t over tau. And then we have this, I as a function of t is I0, e to the negative t over tau. Now, these both have a battery in them, but it will work just fine in this case. We can't derive this equation, but we know that the current's going to decrease over time because there's a resistor in there, and there's nothing giving energy to it, right? That resistor is going to dissipate energy. That's going to decrease the current. It's going to have to decrease. This one increases over time. This one looks like this. I is a function of time, and it goes like that and reaches some maximum. This one starts off with some value, I0, and goes, and they actually make those noises. So we want to use this. If we use this, it will work. And for both of these cases, the time constant, tau, is L over R. So I know L, I know R. And so we want to find out the time for the current to get to 5% of its original. So we can write this, let's put this over here. I don't need that anymore. I have to choose what to erase and what to not erase. So tau is, and that's the Greek letter tau, it's not a T, is that. And I can write this as 0.05 I0 equals I0 e to the negative t over tau. Because that's whatever current I started with, it actually doesn't matter. Now I'm at 0.05%. If you wanted to say, 5% of that, that's fine, but you don't need to, because those two values cancel. So now I can get rid of this. I've already used those. That cancels. I want to solve for time. To get rid of the exponent, I'm going to take the natural log of both sides. So the natural log of 0.05 is going to be negative t over tau. And now I can solve for t. T is going to be t. T is negative tau, natural log 0.05. So tau is going to be 1.5 over 2. Okay, so let's calculate tau. Or let's just put that in there. So t is negative tau, which is 1.5 over 2 times the natural log of 0.05. Calculator. Okay, drop 1.5 enter 2 divided by 0.05 natural log there's natural log times, and I get 2.25 seconds. It won't give me the thumbs up. Come on. There you go. Okay. Now we want to find the average power dissipated. So this is a little tough, right? Because the current's not constant. And if we want to think of it like this, here's the current as a function of time. And it goes like that. Well, I can't calculate the power because it's not a straight line, but I can calculate the average. Let's just calculate that current and that current. And then I need that time and that time. And I can use the definition of power. I'm trying to think. I could do IR squared. I think this should work. Or I could do energy stored as divided by time. So these are the two ways I'm thinking about it. Of course, I didn't think this thing through. Let's go with this definition. Power is I times V, but V is IR. So it's going to be I squared R. And for the average I can say P average is going to be I0 plus 0.05 I0. That's divided by 2. And then square that. And then multiply by 2. Let's do that. Okay, so this is going to be equal to, well, I can have the 2 squared is 4 and the 2 right there. And the I0 I can pull out. So I have I0 over 2 and then 1.05 squared. And that's squared. That should work. Okay. And that's 5 amps. So it's going to be equal to 25 over 2, 1.05 squared. See how I can simplify it a little bit? Okay. 25 1.05 squared times, oops, I did that already, 2 divided by, I get 10.7 watts. Now let's think about this the other way. Power is the change in energy with respect to time. So this is going to be U2 minus U1 over delta T. And I know delta T is 2.25 seconds. I don't know if we're going to get the same thing or not. Let's just do it. So U2 is going to be, we can write this as, am I running out of room? No. P is going to be 1/2 L, and this is going to be I, let's put this as 0.05 I0 squared minus I0 squared, right? Because that's the final energy minus the initial energy, and this is going to be all over delta T. Does that make sense? Okay, let's just do this. I can factor out this. Let's put in my values. I'll put it up here. I can factor out the I0 squared. So I have 1/2 times, this is P, 1/2 times L, which is 1.5. And then I factor out the I0 squared, which is 25. And then I have this 0.05 squared minus 1. And then all of that divided by 2.25. Calculator. Drop. 0.5. Enter. 1.5 times 25 times 0.05 squared. 1 squared is 1 minus that, and then multiplied. 2.25 divided by, and I get negative 8.3, which is the power change in the power of the inductor, which would be the power dissipated by this. So here I get something a little bit different, 8.31. But they're pretty close. I had, what was the other one, 10? but let's just go with 8.31 since I didn't write down the other one. I suspect that's what they want you to do. When they write the problems, right? You just calculate the change in time. So couldn't you use that to calculate power? I don't know. If this was a test, I would accept either way. Okay, because it's not really the average power. It's an approximation. That's that.